All right, welcome AP students to your first AP problem walkthrough video. Don't forget these videos are one, they're going to introduce a couple usually conceptual problem walkthroughs through the first half of the workbook, and then I will put a marker of the time that the AP problem walkthrough portion starts in my video description. For grades wise, when I talk about homework, your 5% of your overall grade, what I will be checking is your completion of the AP problem walkthrough portion. And then this initial conceptual walkthrough problem portion that's part of this video is totally for your benefit. However, I will only mark you complete or incomplete for homework based on the second half of the problem, which is going to be an AP based problem at the end, toward the end of your workbook. Of course, if you are not able to watch this video in time, when I do the homework check, you can simply submit proof uploaded into Canvas that you did end up completing that. Don't forget to get the full 10% extra curve on your test. You must complete all AP problems in your workbook. And I'm emphasizing this one more time, the conceptual is merely for your benefit. So let's start with our first half of this video, which is just conceptual, couple problems in the first half of your workbook that is just to help you. And then I will make a marker in the description saying when the AP problem, which I will actually grade or check you on, is starting. So we did just talk about our initial lessons because we did a couple. We're on, of course, one numerical representation, and you've already taken a quiz on it. And then we started on the official AP Unit 1 topics, which was essentially matter and atoms. Okay. And you've covered so far how we categorize matter and its properties. And then we started getting into atoms and isotopes and a couple instruments that we use to experimentally quantify and confirm the existence of certain isotopes, versions of elements with different masses, and describe the atomic nature and specifically the physical nature. Okay, so this first conceptual walkthrough problem is just a quick little overview over mass spectrometry, or reading a mass spectrum, or reading the results of a mass spectrometer. This particular instrument is very useful for identifying isotope abundance and, of course, therefore, the identity of the element that we may not know that we're working with, right? An unknown element. As far as the kinks of how it works, I'm not going to quiz you on that, and neither will the AP exam. But if you're curious about exactly how a mass spectrometer is built, there are plenty of YouTube videos out there, and I might have even hyperlinked one on the notes. So here we see on this mass spectrum, we always have mass over atomic ratio, M over Z. Overall, you can just kind of think of this as mass in general. Okay. And you have relative abundance out of 100%. We send our sample through, it diffracts, it breaks it apart, so forth and so on. And we get these results. And what you're immediately going to notice is that the most abundant isotope for this element is a 90 AMU. So whatever this element is, the most abundant is 90. And it's about 50. Oh, it's about like 52% abundance, relative abundance of this isotope. And then you have a 91 isotope present in about 10%. And then you have a 92 in about 20%. And then, of course, finally, oh, actually not finally, you have a 94, a little bit higher. I would say maybe 22%. And then finally, you have a very small amount of 96 isotope mass at a relative abundance of about maybe 4%. Okay, I don't know if that's actually at 100. Let's see. These are just guesstimates, right? And what we see is that knowing that the average isotope, or sorry, the average atomic mass for a given element is the sum of the relative abundance of each isotope of that atom element, that elemental atom, we can say that, well, whatever the identity of our element is, it's going to be relatively close to 90 because that's the most abundant isotope, the greatest contributor, the most likely to be observed in the universe. But we also have higher values of 91, 92, 94, and up to 96 that is going to shift that value or that average atomic mass a little bit higher. So honestly, this is a little bit of a guessing game without the super exact, right? Notice these are just generic graphs that you are going to create guesstimates on. But what you can conclude is safely that this element is either zirconium or niobium, okay? Zirconium or niobium. That's not a very common element used. All right. The final answer is zirconium. If you were to actually look up the values of zirconium's relative isotope abundance, it would actually match this. But on the AP exam, if they give you a problem like this, it'll be far more obvious. So this is just practice of reading. So next conceptual question is about wave particle duality and the photoelectric effect. So question 21 says a laser emits light with a frequency of 4.69 times 10 to the 14th hertz or 1/seconds, right? And what is the energy of one photon or particle of light of the radiation from the laser? So here you're just simply doing a plug and chug problem where I give you the relative information that you need, you plug it into the equation necessary, and you chug out the calculations to find your answer. Here we're quantifying the matter, we're quantifying the matter of energy, which is super cool. I love wave particle duality. So what you would do here is you know that you are given the frequency, okay, which is nu, and it looks like a V, but with a little tail. And you're asked to find energy, and you know that H is Planck's constant. Planck's constant is 6.626 times 10 to the negative 34 joules per second. Okay. And so all you do is you have two of the variables, you have one unknown, you plug it in, real basic for those of you that are really good at math, which I was most of you actually based on the pre-diagnostic test. And you say that the energy of this photon is going to be equal to Planck's constant times the frequency emitted when this photon was emitted. So 4.69, or this frequency observed when this photon was emitted, times 10 to the negative, or sorry, to the positive 14 all over seconds or per second, right? Hertz. And what you see is that you get the energy equals, okay, 3.11 times 10 to the negative 19th joules for one photon or per photon. All right. Don't forget any derived unit, right? It's or implicit derived unit, right? Because we're saying energy is 3.11 times 10 to the negative 19th joules for this one photon, right? For one photon could also be turned into a unit conversion. So don't forget that. This could also be written as later if there was a follow-up question, which often happens, as you'll see in in part A. If the laser emits a pulse of energy containing 5.0 times 10 to the 17th photons of this radiation, what is the total energy of that pulse? So what we're going to do is we are going to say, well, I know that I'm initially, okay, whatever they give you initially, start there, especially when you're setting up your unit conversion / dimensional analysis, okay, mathematical processes. You want to start with the given. So you know that you have 5.0 times 10 to the 17th, okay, photons. Now your previous work above told you a new relationship, a new unit conversion, a new equivalence factor. And you know that, well, if I have that many photons and every photon, okay, has 3.11 times 10 to the negative 19th joules of energy per photon, what we see then is our total amount of energy is going to be 0.16 joules. Now, something I want to make sure that you're tracking as well at the same time is your sig figs for your final answer. So the first answer for Initially, the initial question was in 3 sig figs based off of the 3 sig fig provided value. The next question, it was 2 sig figs. So I have a 2 sig fig final answer. And let's go ahead and move on to part B. If the laser emits 1.3 times 10 to the negative 2, okay, joules of energy during a pulse, how many photons are emitted? So here, again, we're going to take our previous work and we're going to turn it into a math tool, the relationship that we derived. So I know this time that I'm given, right? We always start with our given 1.3 times 10 to the negative 2 joules of energy. And I got to figure out how it relates to photons. Well, I know that for every 1 photon, I produce 3.11 times 10 to the negative 19th joules of energy. And this time we flip it so that the joules cancel, right? Your old units cancel, and you're using an established relationship between the two to land you at the final unit of measurement, which in this term is our photon. And we get that if we have this much energy initially being emitted, and we know that 3.11 times 10 to the negative 19 joules is emitted per photon, we have approximately 4.2 times 10 to the 16th photons being emitted to produce that initial amount of energy. And again, we check, are we in the correct sig figs? Yes, we are. So now let's go ahead and scroll on down to, I believe, a couple AP problems now. So I will again put the timestamp in the description for you to get to this point. These questions are what I'm going to check for the next day for homework completion and what you would submit if you did not have it ready in time when I checked in class. So we're going to scroll all the way down to question 2, short answer FRQ, and we're just going, or short FRQ, which by the way is worth 4 points on the AP exam and is expected. The AP delegates only about 9 minutes to these questions. And we're just going to do part D because that's the only part that you know how to do in this. So here in question 2, the background is that you have a new element with a specific atomic number of 116. And it was named livermorium, LV, and it's radioactive and short-lived, so it's got a short half-life, and its chemical properties and reactivity should follow periodic trends. That's kind of your background to this question. We're going to skip over A, B, and C, and because you're going to learn about periodic trends in the following classes, and we're going to talk about this one. Shown below is a hypothetical mass spectrum, okay, for the sample of, what is it called again? Livermorium. Containing 10 atoms. So you have a sample of 10 atoms that they shoot through a mass spectrometer, and it asks you, using the information on the graph, determine the average atomic mass of livermorium in the sample to 4 sig figs, 4 significant figures. So what you're simply going to do is you're just going to do basic math. So you know that the first isotope, okay, is 291.2, and so nice of them, they give you the exact atomic mass values that they're having you work with. So 291.2, and you're going to multiply it by its relative abundance, which is about 2/10. 2 out of the 10 atoms had this, 2/10. And when I say about, I definitely meant exact. There's no half an atom. Plus, okay, 292.2 times its relative abundance, which was 3/10. Plus, sorry, I kind of ran out of room. 293.2 isotope with times its relative abundance of 5/10. And that is going to give us a total of, when we just do a summation, we're going to get that the average atomic mass based off of this 10 atom sample for this newly discovered livermorium element is 292.5 AMU, atomic mass units, and it is into the correct final report of 4 sig figs. Okay, so let's go ahead and move on to question 3, another short FRQ that should as a whole take you about 9 minutes to do. However, since we are just at the beginning stages of our learning, we're only going to do part A. But the background is that 3 stable isotopes magnesium are magnesium 24, magnesium 25, and magnesium 26. And that there's a rock sample taken from another planet with a different distribution of these isotopes. So we have different relative abundances on another planet. A partial mass spectrum for the magnesium in the rock sample is shown below. Draw a line on the graph to show the mass of the missing isotope and its percent abundance. Okay, so here, we need to realize that we don't have a 24. So we have all three stable isotopes still found on the other planet, but the current mass spectrum has only 25 and 26, isotope 25, isotope 26 mentioned. Now, we do know that there's a different relative abundance for each. So we know that the sum total of abundance of 24, 25, and 26 must equal 100. Currently, we have isotope 26 on this other planet for magnesium. And actually, I know the element, so I'll just write it, is 40%. And magnesium 25 on this other planet, based on this rock sample, is 20%. So you know then that the magnesium 24 must be, math, another 40%. Okay? So what you should do is you should draw the 24 little bar of 24 mass, isotope with a mass of 24 at 40% abundance. Okay, and B, use the completed mass spectrum to calculate the average atomic mass of magnesium on the other planet. You guys should be very familiar with this. Again, it is basic plug and chug. So you're just going to multiply the relative individual isotopes by the respective abundances to find this average atomic mass. And don't forget to report to the proper sig figs. So what we have here is we have 24, what we just learned, times 40%, or to make it more mathematically correct, an equation 0.4 plus 25 times 0.2 plus 26 times 0.4. And you're going to get that this equals a total of, and I'll actually just put equals, average atomic mass of 25 AMU, assuming that, again, these are all whole numbers and these were very beautiful abundances that require no decimals themselves. So that's why we see that our average atomic mass here doesn't have any decimals. And according to sig fig wise, we're only in 2 sig figs. So we are staying true to the data. Okay, so really good work, you guys. Be prepared to show me page 16, 3A and B, and page 15, 2D tomorrow for homework completion. Excellent work. Bye, guys.